Hey guys, Mr. B here, and welcome to Chapter 12. This chapter is going to be about stoichiometry, which is a really funky sounding word, but basically all we're going to be learning about in this chapter is how can we use chemical equations to calculate the amount of material either needed in a reaction and for it to start or go, as well as how much product can we make. So last chapter, in Chapter 11, we were learning about chemical reactions and how they're sort of like recipes. And in this chapter, we're basically going to be learning how do we use those recipes to then calculate amounts of stuff. So this chapter is going to involve a lot of previous skills that we've learned already through the course, writing chemical formulas and naming chemical compounds, doing the math behind the conversions and all that stuff. So it's really just a culmination of a bunch of skills. There's not a whole lot of new information, actually. It's more just application and learning how to apply the stuff we already know. So let's begin here with using balanced equations. So how is a balanced equation like a recipe? So in Chapter 11, we talked about this, but I mentioned how in a chemical equation, we have a balanced chemical equation and a skeleton equation. And sort of like a recipe, when you write out a chemical equation and it's balanced, it tells you how much of each material you need, sort of like a recipe card, right? The skeleton equation will just tell you, well, here's what you need, here's the materials, but not how much. And a recipe, of course, gives you quantity. So here's an example just using like maybe a chemical equation for making a tricycle. In order to make a tricycle, you need one frame, one seat, 3 wheels, 1 handle, and 2 pedals. And if you put all of these reactants together, you'll make one product, which would be a tricycle and has a chemical formula of FSW3HP2. Okay, so this is a balanced chemical equation in a sense, and this is what we could use to then determine how many pieces we would need to make a tricycle. So let's take a look at using balanced chemical equations then when it comes to math. So a lot of times we're going to use chemical equations to calculate how much reactant we need or how much product we can make in a chemical reaction. Okay, now this is really important because when you're dealing with chemicals in an actual chemical laboratory, in a real chemical setting, you don't just want to mix a bunch of stuff together and just make as much as you just happen to make. One, chemicals cost a lot of money, so you're just going to be wasting money as you just pour a bunch of stuff together. And if you're, of course, working at a company, your boss is not going to like that. So also, whenever you're doing a reaction, you might be specifically trying to make a certain amount of stuff. Like, I need exactly like 10 grams of this material. So how much should I start with to make 10 grams? Okay, and all of those calculations, again, in chemistry is called stoichiometry. So let's take a look here at doing an example, and then we can understand it better when we jump into more of the chemical reaction stuff. So here's one using that tricycle equation we saw earlier. So it says, in a 5-day work week, Tiny Tyke is scheduled to make 640 tricycles. How many wheels should be in the plant on Monday morning to make these tricycles? Okay, so in order for us to solve this problem, and pretty much to solve any of these problems in this chapter, we're going to need to know the balanced chemical equation for this reaction. Now, this is what they gave us on the previous slide. So I'm actually just going to copy and paste this. Okay, so we have this here. And let's insert a text box down below so we can do some typing. Okay. All right. So let's make this a little bit smaller too, just that way, again, we have some space. All right. So we have to make 640 tricycles. All right. So this is the number we're going to be starting with. Okay. So we're going to be starting with, let's make our font a little bit bigger. So 640 tricycles. Okay. And the question is, how many wheels should be in the plant on Monday morning to make these tricycles? So we're going to have 640 tricycles to start with, and we are going to get an answer in wheels. Okay, now we're going to set these up just like we did in Chapter 10 when we were learning how to do conversions between units. All right, now this is what we're going to start with unit-wise, is we're going to end with unit-wise. The question, of course, then is, well, what's the conversion factor, right? If we're going to go from the units of tricycles to the units of wheels, we need to know the conversion factor, right? How many of each one do we need? Well, this is where the chemical equation comes into play. For every 3 wheels, we can make 1 tricycle. Okay, so that's our conversion factor. I'm going to write it here in parentheses. So 3 wheels for every 1 tricycle. Okay? So if we set up our math, using dimensional analysis, we are starting with 640 tricycles, which means that we need to multiply this by 3 wheels over 1 tricycle. This will cancel out the unit of tricycles and get us into the unit of wheels. And then, of course, all we have to do is just take 640 and multiply by 3. And we get 1,920 wheels should be in the plant on Monday morning in order for them to make 640 tricycles. Okay? So, if you are one who struggles with this conversion stuff and you don't understand how to cancel out units, you might want to go look back at Chapter 10 material. There are videos in Schoology you can watch. I'm not going to go through that process. I've done that already. So go look and watch those. Otherwise, as always, there's going to be, time where you can chat with me like in person over Google Meeting. So, okay. So in terms of what quantities can we interpret balanced chemical equations? Now, we can use chemical equations, of course, to determine how much material we need of different things, but the units that we can use them on is actually very, very versatile. So we can interpret a balanced chemical equation in these quantities: number of atoms, number of molecules, number of moles, number of grams, number of liters. Okay, pretty much all of the units that we've learned about in this course, we can interpret a balanced chemical equation in those units. Okay, and it's important to understand that, because that means that when we're using a balanced chemical equation, we can calculate a lot of different amounts of material, right? Because, of course, not every material that we're dealing with in real life, maybe we can't measure it in grams because it's like a gas or something. So maybe we got to measure it in liters, okay? It's a volume. Or maybe we specifically want moles, all that stuff. So here's a reaction, which is N2. So 1 N2 plus 3 H2 makes 2 NH3s. Now we can interpret this in terms of atoms, right? 2 atoms of nitrogen plus 6 atoms of hydrogen will give us 2 atoms of nitrogen and 6 atoms of hydrogen in our products. Okay, pretty simple. Again, we can just see that by visually looking at this image. We can interpret this in terms of molecules. 1 molecule of N2, okay, this is a molecule, 2 atoms bonded together. That's 1 molecule, plus 3 molecules of H2, right? Again, 1, 2, 3 molecules of H2 will make us 2 molecules of NH3. Okay, so again, here's 1 molecule of NH3, here's a second one. So we can interpret this in terms of molecules. And it's important here to realize now that these are in ratios. For every 1 molecule of N2, we have 3 molecules of H2. So that's a 1:3 ratio. And for every 1 molecule of N2, we'll make 2 molecules of NH3. That's a 1:2 ratio. So if we multiply this by 10, we could then see, well, every 10 molecules of N2, we're going to need 30 molecules of H2, right? So again, it's a 1:3 ratio. And for every 10 molecules of N2, we'll make 20 molecules of NH3 because it is a 1:2 ratio. Maybe instead of thinking of it in terms of tens, what about a mole's worth, right? If we had 6.02 times 10 to the 23rd molecules of N2, that would be a mole. Then we would need 3 times that amount of H2. And then we would make 2 times that amount of NH3. So we can interpret this in terms of moles, right? 1 mole of N2 1 mole of N2 will then need 3 moles of H2 and will make 2 moles of NH3. If we know moles, we then can convert that into grams. The molar mass of N2 is 28 grams per mole. So if we have 1 mole of N2, that means that we would need 28 grams of N2 if we were to measure it for mass. And if we have 3 moles of H2, the molar mass of H2 is 2 grams per mole. So that would be 6 grams of H2. So 34 grams total of reactants. And if we're going to make 2 moles of NH3, the molar mass of NH3 is 17 grams per mole. So 2 moles times 17, that gives us 34 grams of products. Now it's interesting to note here that the total number of mass of reactants, 34 grams, is the same as the total mass of the products. And that's important because, of course, we do have to obey the law of conservation of mass, which means that if you are starting with 34 grams of reactants, you should be ending with 34 grams of products, because you can't magically create more mass and you can't just delete mass either, okay? Of course, we could assume these are gases, and we could do volume. So molar volume is 22.4 liters. So for 1 mole of N2, that would be 22.4 liters of N2. If we have 3 moles of H2, that would be 22.4 liters times 3 for volume of H2. And if we make 2 moles of NH3, that would be 2 22.4 liter amounts of NH3, right? So again, as you can see here, we can interpret this equation in a lot of different units, which is, again, important because of the fact that you might need to be able to convert and use a lot of different units when you're measuring things in chemistry. Okay, not everything can be measured in grams or moles or molecules or liters, right? It just depends on what you're dealing with. So, all right. So let's take a look at mass conservation in these chemical reactions. So what quantities are conserved in every chemical reaction? And of course, we know that that's mass in atoms, right? Law of conservation of mass says you cannot destroy matter. So grams will always be conserved. If you're starting with 15 grams of material, then you better be ending with 15 grams of material. Atoms, same thing. If you're starting with 100 atoms of one material, then you better have 100 atoms at the very end when you're done. Okay, so mass and atoms are conserved in every chemical reaction. We know this. That's where balanced chemical equations come into play. So let's take a look at some examples here now with chemical stuff rather than, tricycles. All right, so it says hydrogen sulfide, which smells like rotten eggs, is found in volcanic gases. The balanced equation for the burning of hydrogen sulfide is, and it's given here. So it says, interpret this equation in terms of A, numbers of representative particles in moles, and B, masses of reactants and products. All right, so let's insert a text box here so we can do some typing as usual. Let's change our font to red. Let's change our color to red and our font size to 18. Okay, so for letter A, if we interpret this in terms of representative particles, okay, H2S. Actually, let's write the equation first here. So H2. Oh, did not mean to do that. There we go. H2S, or 2, I should say, 2H2S plus 3O2 goes to 2SO2 plus 2H2O. And I'm leaving out the G's for gases just because that's just a physical state. It doesn't really have any effect on our reaction. So, all right, we're going to put this more in the middle here so we have some space to type underneath. All right, so representative particles. All right, so H2S, that is a molecule, technically, because we have hydrogen and sulfur, which are nonmetals. So basically, this would be 2 molecules of H2S plus O2, that's also a molecule. So 3 molecules of O2. Okay, now you'll notice here that I'm using 2 molecules of H2S because there's a 2 in front, and 3 molecules of O2 because there's a 3 in front. Okay. Then we get SO2, that's also a molecule because sulfur and oxygen are 2 nonmetals, so that's a molecular compound. So 2SO2 plus H2O, also molecular compound, because hydrogen and oxygen are nonmetals, and these would be the representative particles for these compounds. So 2 molecules of H2S plus 3 molecules of O2 will give us 2 molecules of SO2 plus 2 molecules of H2O. Okay, and again, I'm getting these numbers just by looking at the balanced chemical equation and using the 2, the 3, the 2, and the 2. Okay, all right, so that's representative particles. Then we also have to write this in moles. So moles and molecules, even though they're not the same unit, can pretty much be interpreted the same way. Because remember that a mole is just a very large number of molecules, okay? But the ratio is still the same. So for every 2 molecules of H2S, that would be 2 moles of H2S. plus 3 moles of O2, we would get 2 moles of SO2 and 2 moles of H2O. Okay? So again, moles and molecules are not the same unit, but when you're reading a chemical formula, moles and molecules can pretty much be read the same way. Okay? It's the same numbers. In terms of mass, okay, so they want us now to determine this in terms of grams. So for us to do this, we need to know molar mass. So if we look on the periodic table and we find the molar mass of H2S, and you would need to look at a periodic table. I know these numbers off the top of my head, okay? So just bear with me here. Otherwise, you'd go look on the periodic table, find the molar mass of H2S. So let's write it down below here. So H2S is 34 grams per mole, okay? Hydrogen is 1 gram per mole, and sulfur is 32. So 2 hydrogens is 2 grams, plus 32 is 34. Oxygen, O2. Oxygen is 16 grams per mole. There are 2 of them here, so that would be 32 grams per mole for the O2s. For SO2, we have 32 from the oxygens, and sulfur is also 32. So this is 64 grams per mole. Again, you would need to look on a periodic table to calculate these. I just know these numbers off the top of my head. Okay, so please understand here that I'm kind of skipping some steps just because to make it faster. And then water is about 18 grams per mole. Oxygen is 16 grams. Hydrogen is 1 gram. There's 2 hydrogens. That's 2 grams plus 16. That gives us 18. So for us to determine our masses, we would take 2 times 34 grams for the H2S. Okay, so 2 times 34 is 68 grams. So 68 grams of H2S plus 3 times 32 grams, okay, for the oxygens. So 3 times 32, that's 96 grams for the O2. For SO2, we're going to take 2 times 64 grams. Okay, so 2 times 64. That gives us 128 grams of SO2. And then 2 times 18 grams for the water. This gives us 36 grams. This gives us 36 grams for the H2O. Okay. All right. Now, one thing we can do to check and make sure that this looks right is if we add up our reactants and the total mass we have there, and we add up our products, they should be the same or very close, based on rounding. So 68 plus 96, that is 164 grams of reactants. And 128 plus 36 is 164 grams of products. Okay, so we have the same amount of reactants as we do products, which means that we did our math correctly because we should have the same, right? Law of conservation of mass says we should have the same. So this is our answer for this problem, okay? All 4 of these things. We are interpreting this equation in those different types of units. All right, so that is it for this section. Hopefully, of course, that makes sense. But as always, if you have questions, please reach out to me so that I can help you. I'm always open to do so. All right, guys, that's it for this one, and I will see you in the next video. Bye.